Look at our world from a great distance from the silent vantage point of space. You see a sphere of swirling white clouds, deep blue oceans, continents of brown and green. Around its edge, a delicate, almost imperceptible halo, a thin, blue line. This is our atmosphere, the air we breathe, the shield that guards us, the blanket that warms us, the boundary between the vibrant, living earth and the cold, silent void of space. Imagine a slow, silent catastrophe, the thin blue line beginning to fade. Watch the vibrant aura thin, dissipate, and drift into nothingness, leaving our planet exposed. This is the day our shield disappears. The atmosphere, a vast ocean of gas held by gravity, mostly nitrogen, about 78%, oxygen, about 21%. The remaining 1% is a cocktail of gases: argon, carbon dioxide, water vapor. It extends hundreds of kilometers upward, but most mass sits in a layer thinner than the skin of an apple. This thinness is deceptive. Within it, all our weather is born, all our sound travels. The very first and most immediate consequence of a disappearing atmosphere is a catastrophic drop in air pressure. Here on the surface of Earth, we live at the bottom of an ocean of air. The weight of all that air above us exerts a constant pressure on our bodies, about 14.7 pounds on every square inch. Our bodies are perfectly adapted to this pressure. The fluids inside us push outward with an equal force. But as the atmosphere thins, this external pressure plummets toward the vacuum of space. The delicate equilibrium that keeps us alive is instantly shattered. Without the atmosphere's embrace, the human body would face a brutal, swift end. For any living creature that breathes air, the end would come in seconds. The first sensation would not be the inability to breathe, but a strange feeling in the lungs. With each attempt to inhale, there would be nothing to draw in. The air would be too thin to provide the oxygen our blood needs. Within 15 seconds, the oxygen stored in our bloodstream would be depleted, leading to a loss of consciousness. The lack of external pressure would cause the gases dissolved in our bodily fluids to bubble out. Nitrogen in our blood would form bubbles, similar to the bends, but happening everywhere inside the body at once. It would be a silent, swift, and inescapable suffocation. This is not just a human problem. Every bird in the sky, every mammal on the land, every insect, every reptile would face the same fate. The very act of respiration, the fundamental gas exchange with the environment, becomes impossible. With the air gone, our perception of the world would fundamentally alter. The sky, our beautiful blue canopy, would be gone. The blue we see every day is not a property of air, but of Rayleigh scattering. Molecules in the atmosphere, primarily nitrogen, oxygen, scatter shorter, bluer wavelengths of sunlight in all directions. That scattered blue light fills the daytime sky and drowns the stars. Without an atmosphere, nothing scatters the sunlight. The sky would be permanent black like the moon's surface sky. Imagine standing at midday on Earth. The sun would no longer sit in a blue field. It would be a terrifyingly sharp, brilliant disk set against absolute black space. Stars would be visible all day, glittering coldly beside the sun. There would be no dawn or dusk. Transition from day to night would be instantaneous like a light switch. One moment the ground is bathed in harsh sunlight. The next it's plunged into total darkness and cold. Only the moon and stars faintly visible. Our atmosphere acts as a planetary thermostat, trapping a portion of the sun's warmth and distributing it around the globe. This is the greenhouse effect, and in moderation, it is essential for life. It keeps our planet's average temperature stable and prevents wild swings between day and night. Without this gaseous blanket, Earth's ability to regulate its temperature would be completely lost. The surface would be at the mercy of direct solar radiation during the day and the cold vacuum of space at night. The planet would transform into a world of violent and inhospitable temperature extremes, far surpassing anything we experience today. During the day, any part of the surface facing the sun would heat up rapidly and relentlessly. With no air to scatter or absorb the incoming solar energy, and no wind to carry the heat away, the ground would bake under the unfiltered glare. Temperatures on the sunlit side of the planet, especially near the equator, could soar to well over 120 degrees Celsius, 250 degrees Fahrenheit. The ground would become hot enough to boil water if any were left in a liquid state. Surfaces would scorch, and the very rock and soil would radiate intense heat, creating a landscape akin to a furnace. Then, as the planet rotates and that same location moves into darkness, the change would be just as dramatic and extreme in the other direction. With no atmosphere to hold on to the heat absorbed during the day, all of that thermal energy would radiate away into space almost instantly. The temperature would plummet with breathtaking speed. Within hours, the same ground that was scorching hot would fall to temperatures far below freezing, dropping to perhaps minus 150 degrees Celsius, minus 240 degrees Fahrenheit. Water is the solvent of life. Earth is defined by its vast blue oceans. The atmosphere plays a critical, often invisible role in keeping that water on the surface. The pressure of the air above the oceans makes it more difficult for water molecules to escape and turn into vapor. This process, evaporation, is a constant, but it is regulated by atmospheric pressure and temperature. If you remove the atmosphere, you remove the lid from the pot. The oceans would no longer be held in place. Lakes would no longer be held in place. Rivers would no longer be held in place. A process of planetary desiccation would begin, as Earth's water starts its slow but inevitable escape into space. In the near vacuum of the new environment, the boiling point of water would fall so low that it would essentially be at or below the ambient temperature of much of the planet's surface. In sunlit areas, the oceans would not just evaporate, they would begin to boil violently. Great plumes of water vapor would rise from the surface, a chaotic churning mist that would quickly dissipate into the void. This isn't the kind of boiling you see on a stove. It would be a cold boiling, driven by pressure, not heat. The surface of the oceans would appear to be in a constant, silent turmoil as they gave up their water to space. Over time, this process would cause sea levels to drop precipitously. Centuries and millennia would see the oceans shrink, revealing lost coastlines and turning continental shelves into vast, arid plains. The water that remains would become increasingly saline, a concentrated brine that would be toxic to any marine life that had somehow survived the initial changes. Eventually, the mighty oceans that cover 70% of our planet would be reduced to smaller, hypersaline seas in the deepest ocean basins, and perhaps frozen solid at the poles where the sun's influence is weakest. For any life that miraculously survived the initial suffocation and pressure drop, a new and relentless threat would emerge: radiation. Our atmosphere, along with the magnetic field, is a multi-layered shield. Sun's most harmful emissions, cosmic rays, originating from deep space ozone in the stratosphere, absorbs the vast majority of dangerous ultraviolet radiation. The thicker layers of air below absorb or deflect X-rays, gamma rays, high-energy charged particles. Without this shield, the surface of the Earth would be flooded with a lethal dose of radiation, sterilizing the planet. The most immediate effect would be from UV radiation. The same type of energy that causes sunburn would increase in intensity by a factor of thousands. Any exposed organic material would be devastated. On human skin, a catastrophic, third-degree burn would occur in mere seconds. This intense UV light breaks down complex organic molecules, including DNA. The genetic code of life itself would be shredded. Plants rely on sunlight for photosynthesis, yet would be destroyed by the very energy they seek to harness. their cellular machinery would be torn apart by high-energy photons. Beyond the sun's own radiation, there are cosmic rays. These are high-energy particles, mostly protons, atomic nuclei accelerated to near light speed by distant supernovae and other violent cosmic events. In the face of such a complete and total planetary catastrophe, could humanity survive? The answer is a qualified and very bleak yes. Survival would not be possible on the open surface of the planet. It would depend entirely on our ability to create artificial, self-contained environments, effectively building small bubbles of the old Earth to shelter us from the new one. These habitats would have to provide everything the atmosphere once did: breathable air, stable pressure, protection from radiation, a manageable temperature. Humanity's future would be confined to bunkers deep underground or to sealed domes on the surface. Underground refuges offer the most practical solution for long-term survival. Digging deep into the Earth's crust provides a natural and effective shield against the deadly radiation bombarding the surface. Kilometers of rock would block cosmic rays and solar flares as effectively as our old atmosphere ever did. The surrounding rock would also act as a massive insulator, keeping the habitat's internal temperature stable and protecting it from the wild swings between day and night happening above. These subterranean cities would be dark, confined, and entirely dependent on technology for light, food, and air. On the surface, survival would require building large, airtight domes. These structures would need to be incredibly robust, made of materials capable of withstanding the constant thermal stress and micrometeorite impacts that an atmosphere would normally burn up. Inside, a complex life support system would be needed to maintain air pressure. This journey to an Earth without air is a thought experiment, but it reveals a profound truth about our existence. We live on a planet that is, by cosmic standards, a paradise. Temperate climates, liquid water, breathable air. All of these are governed by an astonishingly thin, fragile layer of gas. The atmosphere is not just the sky above us. It is the single most critical piece of infrastructure for life. It is the shield, the blanket, the lung of our world. Seeing our planet from space, we can appreciate its delicate beauty. The atmosphere's role as a shield is its most dramatic function. It is a tireless guardian, absorbing, deflecting lethal radiation from the sun, lethal radiation from deep space. It is also a physical barrier, burning up millions of meteors every day, protecting the surface from a constant rain of cosmic debris. Without it, the ground would be irradiated and pockmarked and cratered like the moon. This function is so seamless and constant that we take it for granted, forgetting we live under a planetary force field. If a thin layer of gas keeps life alive on Earth, how fragile is our existence really? Well, think about that for a moment.